So in this lesson, I want to talk about one of my favorite examples of centripetal force, and that is the vertical circle. And so here we have a famous stunt done by a motorcycle driver here on the left. I guess it's shown to the right. I don't know why I say to the left there, but whatever. And we want to know, how do we start to deal with centripetal force if we have a vertical circle where we have gravity and centripetal force working together? What's happening here? So let's kind of look at this. The first thing is there are 4 places in the circle that might be interesting to look at. We have the 2 outsides of the circle where really the centripetal force is perpendicular to the force of gravity, where it and the force of gravity are not really related to one another at all. But then we have these other 2 points. What I have 1 and 3. And 1 and 3, we have the centripetal force is opposite the direction of gravity, and in 3, the centripetal force and gravity are in the same direction. Now, I've put normal force in here because really, if we think about moving in a vertical circular track, it's really the normal force pushing up. Remember that centripetal force is not a new force, but rather the net force, or the sum of the forces acting on the object. So let's look at these different locations and look at a couple of these locations that might be useful. Let's make the assumption that we're traveling in this circle, well, at a constant speed, just to make our life a little bit easier. At point 1 on the bottom, what we could say is the centripetal force is equal to the normal force minus the weight. So what this would mean is that the normal force at point 1 has to be the largest. This would mean for you, your perception of weight would be the largest at the bottom of the circle, when you get to the bottom of that circle. At 2, well, the normal force and the centripetal force are the same. It's not related to the weight at all. In 3, the top of the circle, your centripetal force is the normal force plus the weight. What this would mean is the normal force is equal to the centripetal force minus what the weight is. And you could conceivably have the condition here where centripetal force and weight are equal, which means your normal force is 0. You'd be in free fall at that point. This would be the place that you feel the lightest. In fact, on a roller coaster, if you get the normal force to be 0 at point 3, that's really what you're trying to do, because that makes people feel like they're falling out of their seats at that moment. That's what's fun. And again, at point 4, we get the same thing at point 2, that we really have the normal force, the centripetal force, not related to the weight at all. Now, there's one cool question we can ask. What is the minimum speed at the top of the track to remain on the track? Now, if we did conservation of energy, and we started at the bottom of the track, and we wanted to figure out, well, what do I need to get to at the top of the track to get to the top of the track? You might say, well, that's obvious. If I have a speed of 0, I could reach the height of the top of the track. That's fine. But no, it's not. Remember, we have to move in a circle. We have something weird that's happening here, that as I'm starting to move around in the circle, up to here, that would work fine. But the moment I start to do this, odd things start to happen in terms of that idea of motion. In order to stay in this circle, I have to have enough speed to maintain that motion. So the minimum speed to get around the circle is actually when the normal force is 0. So your centripetal force is equal to mg, your weight. Basically what that means is gravity is what's pulling you around in the circle. So if we divide by m, we can actually find the minimum speed is the square root of r times g, the radius of your circle times g. So this means on a roller coaster, this is why you never can come to a complete stop at the top of that circle, because you need to have some forward velocity. And actually that forward velocity, how fast you need to go, depends upon how big the circle is. The larger your loop, the faster you need to be going at the top to continue to move in that loop. And this would also imply that if you have a circle on a roller coaster, that the top of the circle probably cannot be at the same height as the initial height of the roller coaster, the height of the highest hill. It has to be something smaller than that, because you need to have some speed at the top of that, or the speed when you get to the top of that motion. If you're interested in that, we can actually work that problem and figure out what that height is. There is a way you can calculate out that height. Oh, and guess what? We're going to do that. I forgot about this example problem. So we have a block sitting at rest on top of a initial height of 50 meters, and it's allowed to slide down a frictionless ramp that leads to a circular loop. And I want to know, what is the largest radius of the loop to have the block stay on the track through the loop? So we know h is 0 at the top. We know v0 is 0. I don't know vf, I don't know hf, and I don't know rf. I can use conservation of energy, and if this is a frictionless track, the work done by non-conservative forces is 0. Even around the circle, still gravity is the only force acting on the object. You might say, well, what about the normal force? Well, normal force is always perpendicular to motion around the circle. We know the initial kinetic energy is 0, so we can say that's 0. So we have mgh0 equals mgh final plus 1/2 mv final squared. Now, we could divide by the m because the m cancels out, and we get gh initial equals gh final plus 1/2 v final squared. Okay, that's fine. There's two things that we know. From the last slide, we know that v final, the final speed at the top, for the minimum speed or the largest loop, would have to be square root of g times r. So I could plug that in here for v final. And what does h final have to be? Well, if I'm at the top of the loop, I have to be the diameter of the loop up, or twice the radius, 2r. So I could plug that in for h final. And what I end up with is a pretty interesting equation. That I get gh initial is equal to 2gr plus 1/2 gr. Well, guess what? The g's cancel out, and I get h initial is equal to 2r plus 1/2 r, or 5/2 r is h initial. So the radius of your height really needs to be at a maximum 40% the radius of your loop can only be 40% or 2/5 of what your initial height is, 20 meters. What that means is the maximum height you can get to is really, well, twice that, or 40 meters, or 80% of your original loop, original height. So if you ever look at a roller coaster that goes through a loop and you might wonder, why is the loop always smaller than the first hill? This is the reason why. It has to be smaller for you to continue around the loop. So that kind of ends our lessons on circular motion and uniform circular motion. And that kind of wraps up our unit on uniform circular motion and centripetal force.